This video is part 2 of a 3-part series to help you understand the importance of choosing a camera and lens for a Bath Interferometer, the virtual pinhole, and why many lenses won't work with a Bath Interferometer. Back to our diagram from part 1. Because all of the light of the interferometer passes through a tiny point here, we get a virtual pinhole. An optical engineer would call this a stop. I prefer virtual stop or virtual pinhole, but technically it's an ordinary stop. You could put a piece of paper here and put a small hole in the paper, and it would not affect the eyegram. How small can the hole be? It depends on how much the mirror deviates from a sphere, but typically a 2 mm hole is big enough. Why do we care? Well, this means we are looking at our eyegram basically through a tiny hole that is in front of the camera. Using just my fingers and a drill bit, I made a small hole in this black paper. I had to paperclip several pieces of paper together to make the area near the hole dark. As I get my camera closer to the hole, I get less and less cropping, and the camera can see more and more image through that hole. When I'm touching the hole, I have very little cropping. I back away until I'm just barely cropping the top and the bottom, and the lens is about 5 centimeters or 2 inches from the hole. So this lens is great. It's a Nikkor 50mm f1.8D. For those not familiar with f-stops, here's what it does. This is wide open at f1.8, and this is 3 clicks in at f4. You can see that you always want to use the lowest possible f number on your lens. Besides, going to a higher f number will not dim the eyegram at all because the light reaching any pixel on the camera only passes through a very small region of your lens anyway. You'll see that in my ray trace in a minute. When I look through that same pinhole at f4, at the exact same 5 centimeters or so from the hole, the cropping is much more severe. The important thing here is the diameter of the aperture of the camera lens and how close you can get that aperture to the hole. So short lenses with low f numbers will be better in general, but when you get to wide-angle lenses, they tend to start getting longer again. Zoom lenses tend to have the aperture very deep in the lens, so it's hard to get that aperture close to the splitter cube. Zoom lenses tend not to work so well. Here is a zoom lens at 18mm focal length touching the paper with a pinhole. Now set to 50mm focal length touching the paper. Now set to 105mm touching the paper. There are no good options. This is with the f-stop wide open on this lens. By the way, here I show the pinhole is well outside of the cube, but typically it will be inside the cube. If you were really testing an f3 300mm mirror, you would probably want about 8 waves of positive defocus to give you thicker fringes, which is going to move this virtual pinhole a few millimeters to the right. This is a 15mm splitter cube. If you use a 10 or 5mm splitter cube, you can get the virtual pinhole somewhat inside your camera lens, which would be great. As you go for smaller cubes, the 10mm is fine, but eventually you will also need to use smaller laser beams and therefore shorter focal length divergers, and getting divergers with less than a 6mm focal length is hard to do. I haven't been able to find any. Unfortunately, how much an image is cropped when a pinhole is in front of the lens is not published by lens manufacturers, but we can do a worst-case guess where you assume the aperture as at the back of the lens. If you have a lens but not an interferometer, then it's easy to figure this out with some black paper as I just showed you. Once you know how much the lens crops the image through a pinhole, you can use my tools in the next video to see how big the eyegram will be in your camera, and you can see if this virtual stop is a problem. You can move the camera farther from the pinhole to see where it starts cropping the vertical pixels, and note how far you can have your camera from the splitter. Here's a ray trace of a typical DSLR primary lens. Primary lenses are basically non-zoom lenses. Many use what some call a double Gaussian design, with 2 or 3 elements that basically curve like an open parentheses for the left 2 or 3 elements, and like closed parentheses for the right 2 or 3 elements. This is the actual design for the Nikon 50mm f1.8D, which I just showed you, and which came out in 2002. It's focused on an object 2 meters to the left, which is why you see these lines aren't quite parallel. The camera sensor would be to the right. The vertical field of view with a full sensor camera is 27 degrees, or 13.5 degrees up and another 13.5 degrees down. So I enter 13.5 here, and you can see there is a little less light making it through. Maybe 70% as much light, which gives you trivial vignetting at the top and bottom edges of the photos. Now let's introduce our 2mm pinhole, 18mm in front of the lens. Radius 1 millimeter, so diameter is 2 millimeters. Still good. Let's try 25 millimeters in front of the lens. 30 millimeters. Now we will have cropping. So 25 millimeters is about the limit with no cropping. You might think 25 millimeters is plenty of space between the lens and the cube. Well, not when you realize that this front component is set deep inside the lens. The important lesson from this ray tracing is that knowing when it crops is not obvious by glancing at the lens. It's happening at the back of the lens, the last element of the lens. Nikon makes newer 50mm lenses that are much longer and will possibly have worse cropping due to the virtual pinhole of an interferometer. So takeaways. Some lenses won't work well due to this virtual pinhole cropping. To avoid this, use lenses with lower f numbers. Usually f2 is good enough. f1.4, of course, is better if the lens isn't longer. Telephoto lenses are fine, but avoid zoom lenses as they crop badly. Still, some may work for you. Cell phone cameras are mostly not going to work at all. They have tiny apertures around 2 millimeters, and the aperture is deep in the phone, and 2 millimeters is about the minimum the cone of light gets down to. If your mirror to be tested is f10 and has less than a wave of error, and your iPhone is touching the Bath splitter cube, then maybe it will work, except I don't think you'll be able to set the f-stop and the shutter speed and focus manually, all critical features for taking igrams. Please watch the next video, part 3, Tools to help you choose a camera and lens.